So, of course, I would like to again look at the same equation, and again I would like to say something that can I look at something and have a very quick, rapid convergence so that it just converges very quickly. And so I look at it, I say this breaking LHS and RHS being exactly the same terms does not make a lot of good. So what else can I do? Do I observe something which is weird and that can be used? Actually, there is. So US was very easy to solve given these were n linear equations. N equations, n variables. What's the problem? Non-linearity due to the max function. So I write down exactly the same equation again, except for I get rid of this max. So I'll write down exactly the same equation again, except for I will get rid of the max. So I'll say US. Now LHS and RHS will have the same functional notations. So I do not write down a max over A. I get rid of it. So it's just probability of S dash given SA. Out of SA S dash plus gamma times utility of S dash. I didn't get rid of A, so I have to type in something A. So let us say I get rid of A. So let us say I get rid of A. Or in short, I say that the policy is assumed to be known. If policy is known at every point of time, God has told me this is the correct action. If God is telling me what is the correct action, God has given me the policy, go! Remove action, just take the action that God tells you. So that's exactly what I've said. Somebody has told me the correct action. And somebody has told me the correct action, so I just took that action. So now what I do is, so of course there's no real God that has given me the correct action, so I'll have to assume it. So I assume okay, so at any general time t, you assume that you have the policy. So for time is equal to 1 to infinity, so you already have pi t, 0 to infinity. You already have pi t. So if you have pi t, you calculate how n equations, n variables, and the note is given policy equations are linear. Use any linear equation packet solver. The classic thing is, how do you solve it? It's matrix of utilities is equal to this matrix of all the utilities, US0, US1, US2, US3, US4, US5 is equal to product of this matrix, which is the transition probability matrix, times the reward matrix, which is also given, plus discount is just a constant, times another same matrix around over here. So that's just a matrix. This thing, that's what you need to find out. So represent it in the normal form, linear equations, and then do all the kind of matrix techniques in order to calculate what will be the value of the utility matrix value. So utility is equal to something at the RHS. You don't need to do it. So many linear equation packet solvers, they do that for you. So all that the linear equation packet solvers do is, what is a linear equation? So it is AX is equal to B. So what is X? X is A inverse times B it's a linear equation, so it will have things which are of exactly the same format. You don't need to do it. Linear equation packet solvers do that for you. So I can calculate the US. However, what I need is pi. So can I calculate a better policy now? I can actually do it. So I say calculate a better policy pi at time t plus 1 of course s, which is nothing but argmax over a and the same little thing. It's the same equation I wrote previously. So the algorithm is said to have two steps, where this is called as the policy evaluation. Given a policy, solve n linear equations to calculate utility, and this is called as a policy refinement. And the algorithm is called as so I start with a random policy and keep on improving the policy. From a fixed policy, from a random policy, I calculate for that policy the best utility values, n equations, n variables. For those utility values, taking them as constant, I calculate the best policy. For that best policy, I calculate the best utility. For those best utility, I calculate the best policy. For that best policy, I calculate the best utility. For that best utility, I calculate the best policy. It's called as policy iteration because I'm improving my policies. Now, it's the same algorithm. Why should this be better? Why should this algorithm be better? Previously, we were taking continuous variables, so something could improve from 0 to 0.9 to 0.98 to 0.989 to 0.99 to so on. It could continuously improve. Now it's discrete. Up, down, right, left. The moment up action becomes better, you got it. So it's not a continuous it's not a continuous improvement, it's a discrete improvement, and methods are discrete, and discrete methods will have a faster convergence. So best thing. So because my variables are discrete now, I'm improving a policy, and policy is a discrete parameter. So I obviously get, that's how this continuous improvements would be. And here it's just up, down, right, left. So it starts to believe that down is better, and suddenly it believes that up is better, and this happens very quickly. So you've got a very quick convergence. You've got absolutely very quick convergence, but there's a problem. So the convergence is absolutely very quickly. Let me complete over here. So that's a value iteration. And this is a policy iteration. And these are iterations. And remember, these are not times, as in not seconds. So there is obviously a problem still around over here. You look at value iteration. The complexity is, this is the improvement step, so that's a time step. Given so time is taken as a constant, of course. So here, for n states, these are calculating n equations, given all these things up, so it's On. N is normally large, but it's On. So the total time is On times a constant, which is till what iteration do you go? Over here, I cannot write down O Tmax times N because Tmax will become a constant. Here what happens is, calculation of the utility values given the policy n equations n linear variables, this is O of n cube. Why O of n cube? Because you have got this matrix inversion thing. So that's a problem. That's what you got, that's what you need to have, where of course x is your u in this case. And u is very large. So now the one algorithm is n times t max. So the first algorithm is something which is a complexity of on and it's repeated t max times of value iteration. This is something which is on cube. It's repeated t max amount of time, which is policy iteration. Now, even though the t max of policy iteration will be expected to be like this, much less than t max times value iteration. However, on and on cube cannot be compared, so I cannot call it policy iteration really better. It's better in terms of number of iterations. It is not better in terms of the total time taken. It's not better by the number of seconds, which is what matters to me. So can I do something else? Can I just look at it once more? And when I look at it once more, maybe I get a trick. So let's see if I can spot a trick over here. And the answer is yes, I can spot a trick over here. Why was I calculating utilities? Why did I calculate this? Why? Because they were input here. If they weren't input over here, then I wouldn't have calculated it up. And the only purpose of policy evaluation step is to feed utilities over here. However, do I need accurate values of utility of S? No, there's a argmax. So, if you know the argmax well enough, of course, so argmax of approximate values 3, 8, 6 is exactly same as argmax of exact values 3.86251, 8.7293 and 6.1159. The resolution normally does not matter. Practically doesn't matter, theoretically it matters. So what I do is I just calculate the utilities approximately, or I say that on cube, this is the exact algorithm. I say, can I get an approx algorithm which is on and not on cube. So can I make an approximate algorithm for policy evaluation? Can I get an approximation? The trick is approximation is good enough. I don't need the exact values. Even if you lose on a specific iteration, the next iteration the policy will get improved, the next iteration it will get improved. So I don't need the exact values. argmax just needs approximation values. So can I get an approximation algorithm? So I'll say that I will have an algorithm which is modified policy iteration, which will go exactly same as a policy iteration. So I'll assume pi 0. I'll go for t is equal to 0 to infinity. I'll do policy evaluation and I'll do policy refinement. This gives me US, this gives me pi t plus 1 s. So the only change that I make is, normally this algorithm is on cube, and that's the problem. So instead of solving n linear equations, use value iteration. And value iteration is O n times Tmax, which is very large, but when Tmax large is when you need exact values. So I just use value iteration over here. So it can also be seen that the algorithm is a hybrid of value iteration as this step and a policy iteration as this step. If you make this algorithm, so this algorithm is up to you. How much of time do you want to run a value iteration? If you run value iteration too deep, the utility values become so exact, they become so exact that you only need to run policy refinement once. It takes the best values, but you spend a lot of time in value iteration. If you make the value iteration so small that the utility values are useless, so the policy is not good enough. However, whatever you set, the algorithm will be much better than O of n cube. And because of that, this algorithm really derives its advantages from both the algorithm, value iteration to get quick estimates of utility and policy iteration to get quick convergence in terms of the number of steps. So the complexity of both these, the hybrid algorithm is still O of n. So that's O n times, of course, T1 max. And this is exactly O of n. And the entire algorithm is O of n T1 max plus O of n T2 max, where this is T2 and T1 is the value iteration number. So that's an interesting thing. So there's no n cube around over here, and because I only need approximate, this is much small. That's because I only need approx values. Now there's another interesting thing around over here. What we did was that we calculate US and pi s for all s. So the other question is, do I need US and pi s at every iteration for all states S? What if some pi s has already got its best value, some US has got its already best value? Do I still need to calculate it again and again? If I don't, I can get it instead of ON, something which is ON1, which is less than n, maybe much less than n. Some US and pi s will be completely useless. The agent is never going to go to that states. And because agents is never going to go to that states, maybe calculating those are also useless. So can I save in more time? Yes, and the answer is yes, of course. So I do another improvement around over here, and I say is, let me write it intuitively over here. So I apply in another algorithm. So I say in this new algorithm that I heuristically select states S. So just heuristically select states S, and I heuristically apply value iteration or policy iteration. So this is the step of policy evaluation, and this is the step of policy refinement on S. Now I can get all types of heuristics to tell me which are good states, which states don't matter, which states are causing trouble, which states are not causing trouble. In AI, what do? We solve a lot of heuristics. And again, it turns out there are good heuristics available to tell you which are the states that need more work. Like I have heuristics to tell me which are the students over there which need more work, which are the students I could just let them go. So there are good heuristics which are possible, and those heuristics really tell you, okay, these states, and then again, why should I just apply a T1 max and T2 max? Can I again do something which is more adaptive towards how much of value iteration and when do I apply and how much I policy evaluation and policy refinement? So yes, not to be discussed over here, there are good enough heuristics that take care of those kinds of things, and using this combination is how I solve in. Now this grid space was a representation of any state space. So how do I solve in a general problem where the agent is in a stochastic world? How does it decide in all those kinds of actions? That's by using the value iteration, the policy iteration, the modified policy iteration, or the async policy iteration. The inputs are just the reward functions and the so I'll formally define it as a problem. So my inputs are rewards. I always assume them to be available, and the model, which are the probabilities, and my outputs. I only need a policy. I get US as a byproduct. So you don't need US, you get it completely as a byproduct. And then once all of this is calculated offline, you load the robot, you load the agent with the policy, then it says, okay, I'm at this state, I do this action, I'm at this state, I do this action, or the action corresponding to every state is what is accurately known.